Hello, this is chapter 13, Introduction to NMR Spectroscopy. Okay, so I will use this whiteboard here to introduce some concepts of NMR spectroscopy, and we will divide it into a couple of videos. And so in this one, we are just going to talk about what is NMR spectroscopy. NMR spectroscopy, as the abbreviation stands for nuclear magnetic resonance spectroscopy. Okay, so it's nuclear magnetic resonance spectroscopy, and it is one of the most powerful technique which is available to organic chemists. It provides a basic information, or it provides information about the molecular structure of the compound, and if it is combined with other techniques like IR spectroscopy or mass spectroscopy, it becomes extremely useful. Now, NMR spectroscopy involves the study of interaction between electromagnetic radiation, so electromagnetic radiation with the nuclei of some atoms. Okay, so interaction of these with nuclei of some atoms. Now, which atoms are NMR active? Not all of them. Some examples of NMR active nuclei include proton NMR or H1. So hydrogen has several isotopes. This is the isotope which is called as protium, and this is NMR active. That means if you have hydrogen in your molecule, then you can detect it. Carbon 13 is NMR active, not carbon 12. Okay, then another nuclei that is NMR active is N15, nitrogen 15. Remember that these stand for the mass numbers, okay, because they have various isotopes. And fluorine 19, this is another nuclei that is NMR active, and phosphorus 31. These are some of the nuclei which are NMR active. Now, proton NMR and carbon 13 NMR are the most commonly used in organic chemistry, because you know that most of the organic compounds are made up of carbon and hydrogen. So NMR spectroscopy helps us to identify a carbon-hydrogen framework of the molecule. Okay, so you can get to know how many CH3s, how many CH2s or CH part of the molecule is there using NMR spectroscopy. Now, if you have observed this, what I wrote over here, you can see that the nuclei with odd number of mass numbers were the ones which are NMR active. Okay, so the nuclei to be NMR active, it needs to have a property called as spin. Okay, we call it as a nuclear spin. So if you consider the nucleus of a hydrogen atom, which has got only one proton, right? Hydrogen has only one proton. There are no electrons and no neutrons in here, right? So this proton can be considered to be spinning. Okay, then that is what is called as a nuclear spin. And if you recall from physics, that a spinning proton can be viewed or thought of like a small magnet, right? If any charged particle that spins will create a magnetic moment, and you can think of this behaving like a small magnet with a north pole and a south pole. Okay, so same, you can think about each of the other atoms. We are taking hydrogen as an example because it is the simplest atom with just one proton in its nuclei. Okay? Now imagine that if you subject this proton to an external magnetic field, which has a north and a south pole. Okay, then this proton, which is itself like a small magnet, will align itself either along the magnetic field or against the external magnetic field. Okay, so let's consider a sample of a molecule which say contains a few protons. Okay, and they are all aligned randomly in all directions. Okay, that is when there is no external magnetic field. Okay, but say for example I take this sample and place it in the vicinity of an external magnetic field. So this is an external magnetic field. Then what can happen is some of these will align along the external magnetic field, and some of them will align against the external magnetic field. Okay, so if you let me change the color here, and let's represent this external magnetic field by this blue color. Okay, and the protons, say 3 of them aligned like this along the external magnetic field, and say 2 of them align against the external magnetic field. Okay. So these two states of the these two spin states are represented as alpha and beta spin states. Okay, so let's redraw this. Okay, so the two spin states can be represented as the alpha spin state and the beta spin state. Okay, and remember, the alpha is the lower energy one, the beta is the higher energy one, because the one that aligns parallel to the external magnetic field. So if this is my external magnetic field, the one that aligns parallel to the external magnetic field is lower in energy, and the one that aligns against the external magnetic field is higher in energy. Okay, so this is a plot of energy. Maybe we should use a different color, so let's put this in red color. Okay. Oops, not so good. Okay, so let's put this more clearly. Okay, so this is my energy scale. Now the two spin states are not equivalent in energy, and the difference in energy is represented as delta E. So when a nucleus occupies the occupying the alpha spin state is subjected to electromagnetic radiation, and absorption can take place. Okay, and if the energy difference is equivalent to the energy gap, or the radiation has an energy which is equivalent to the energy gap between the two spin states, then absorption can occur. Okay, so if you have a radiation corresponding to the difference in energy between these two states, then absorption of energy can occur, and this causes the nucleus to flip to the beta spin state. Okay, so this proton absorbs energy and flips to the beta spin state, and this is what is said to be a resonance. So the nucleus is said to be in resonance with the external magnetic field. So that is why this term nuclear magnetic resonance has come by. So when a strong magnetic field is employed, the frequency of radiation typically falls in the radio frequency region, okay, of the electromagnetic radiation. You know that in an electromagnetic radiation there are radio frequency, ultraviolet, visible, X-rays, gamma rays, and many other radiations, right? So the difference in energy here, in this case, falls in the region of radio frequency, and hence typically the frequency of radiation that the that is absorbed is in the radio frequency region. Now we can also continue to talk about this delta E a little bit more. That the it depends, depending upon what kind of external magnetic field we have, the energy gap can be small or big. Okay, so if you subject the nuclei to a weak external magnetic field, the difference in energy delta E would be small. And if you subject it to a strong external magnetic field, then the difference in energy would be large. The strong magnetic field employed in NMR spectroscopy are generally produced by passing a current of electrons through a loop which is composed of superconducting materials like copper. Okay, so generally the NMR spectrometer. Here I have a picture of an NMR spectrometer, and this is how it looks like. It has like the inside view of the spectrometer is shown here. So generally what we have is like a big tank of liquid nitrogen. You have a superconducting magnet here, which is like a copper coil, and it is a really superconducting copper coil, and it creates a magnetic field. This is cooled by we have to maintain a very low temperature in the container. So what we do is put a nitrogen jacket outside, and then within it there is also a helium jacket. So they almost have a very extremely cold environment, so that the inside is kind of maintained as around 4 degrees above absolute zero. Okay. So this extremely cold environment is needed to generate keep this superconductors cold, and these superconductors then generate a large magnetic field for NMR spectroscopy. So in a typical Fourier transform or FT-NMR spectrometer, this is where you keep the sample. So I have a picture of a NMR tube where you put your sample and then dissolve it in an appropriate solvent. I'll talk about the solvent in a little bit here. And then all the protons in the sample are excited simultaneously, and they begin to come back to their original spin states. Okay, so like we showed in the previous slide page, how the protons from the alpha state, they move to the beta spin state, and then when they relax down to their original spin state, this is what is called as proton decay, and it will release a particular energy in a particular way, and that would be in the form of an electrical impulse, which is then received in this receiver coil. Okay, then the receiver coil records this as a complex FID, or a free induction decay, which is a combination of all the electrical impulses that are generated by each type of proton. And the FID is then converted into a mathematical, converted into a spectrum using some mathematical techniques called the Fourier transform. And then what you see is a NMR spectrum. Now, for preparing the sample, you generally need what are called as deuterated solvents. Okay, if you use normal solvents like the ones that are shown here, like C6H6 or CH2Cl2, methylene chloride, or acetone, what will happen is that these have protons in themselves, and then the spectrum will be saturated with protons of the solvent. So we use what are called as deuterated solvents, where the proton is actually replaced by the deuterium isotope of proton, and that now deuterium also has a nuclear spin, but they absorb radiation over at a very different range of frequencies than protons do. Therefore, these can be safely used as solvents to detect the structure of your molecule. Okay, so here we have a like a butane, and you can find out the NMR spectrum of butane by using any of these solvents. It will well, butane is a non-polar compound, so it will better would be to use something like benzene, and then you can actually put it in the sample tube and place the sample tube in the NMR spectrometer. Let it run for maybe like 16 scans or something, which is more than enough for a proton NMR, and you will get a signal pretty quickly, and telling us about the type of protons that you have in this compound. Same thing you can do with carbon NMR. Now there are 4 carbons in this molecule, so you can actually get the carbon NMR for this molecule too. This is in general a little bit introduction to NMR, okay, the techniques. I will not go into too much details about the techniques of NMR, because what I actually want to focus is how to analyze a proton and a carbon-13 NMR, which we will talk about in our next couple of videos. Okay, so in the meantime, make sure that you read your textbook regarding this first part of NMR techniques, and try to understand the details of them. Okay, thanks.